Hey,
How you doing?
doing good. How about you?
Good. So what do we got going today?
We had I had a test. It ended up, here.
Gonna
Is there any way this review to you?
sure. Do you know where to send it?
Yeah, here.
David Cowan, 1949 at gmail.com.
Okay, here, one sec. I gotta pull it up and everything.
Okay. What kind of stuff are you covering now?
Right now the next unit we're moving on to is transformations to graphs.
Okay.
Sorry, could you give me the email again?
Here, let me write it. Once you put it in, it should stay in your phone so that you won't have to do any more than 2 letters.
Yeah.
There's my email. That's the best email to send it to.
You should be getting it.
Okay. Got it. What kind of file is this?
Should be a PDF.
Yeah. Hmm. Interesting.
That's strange. Here,
Let me just try clicking on it. Yeah, that works better rather than downloading it. That
that's strange.
works better if I just click on it. So you cannot use your calculator here.
Mm-hmm.
So let's talk about this function. X to the third minus 4x squared plus 4x. Sketch an accurate picture and label at least one point between each x-intercept. Okay. What's the first step to sketching an accurate picture here?
Well, I do know that the right side is going to be going up and the left side is going to be going
What
downwards.
else can you do with this function? Always think about, can you factor this?
Yes, you can.
Okay, what's the first step of factoring it?
Taking out an x.
Okay, what does that leave you with?
X squared minus 4x plus 4.
How do I factor that quadratic?
It would just be x squared. No, x in one, x in another, and then minus 2 for each.
Correct, and that gives you the proper quadratic. So, if I'm going to graph that, where are my x-intercepts? There's 2 of them.
It'll be at 0 and positive 2.
Okay. What else does it ask for? Is that it? Let's see. And label at least one point between each x-intercept. Well, it doesn't quite answer the problem. In other words, we know that one x-intercept is there with multiplicity of 2, and one x-intercept is there. So most likely what this thing looks like is that. In other words, when you have multiplicity of 2, do you know what I mean?
Yeah.
When you have a multiplicity of an even number, it kisses the x-axis. It does not go through it. Very important concept to remember. In other words, if this was x minus 2 times x minus 2 times x minus 2, it would go through that point. But the fact that it's even multiplicity means that it's going to kiss the x-axis only and go up from there.
Okay.
So they said label one point between the x-intercepts. Well, there's only two x-intercepts.
So would you just split the difference and do 1, plug in 1?
That's probably the easiest one. So what is that point right there?
It should be 1 minus 4 plus 4. So it should just be 1.
Correct.
Once you get it to the door, it'll go. This is one sentence right now.
Okay, let's have a look at number 2. This is an interesting one. Let me think about this one for a second. Well, this is not that easy of a function to figure out how to graph, but a good place to start is always the x-intercepts and the y-intercepts. So what are the x-intercepts? If y is equal to minus that times that, what are the x-intercepts?
Would it be -1 and +1?
Well, the x-intercepts are where y equals 0, correct?
Yeah.
So I have 0 equals minus x plus 1 squared times x minus 1 squared. Now I can divide both sides by -1 to get that. And then what makes that 0? Well, what two values of x make that thing 0? Yeah, you gave it already. +1 and -1. In other words, for that thing to be 0, either that has to be 0 or that has to be 0. And the only values that make both of those 0, or either one of them 0, are -1 and +1. Alright, so immediately I know I have some x-intercepts there. Right there and right there. Now, is this a quadratic, is it a cubic, or is it a quartic?
I have no idea.
It's a quartic. Notice that this left term becomes a quadratic, x squared. The right term becomes a quadratic, x squared. And when you multiply them together, you get x to the 4th. So it's definitely a quartic. Now, quartics have maybe 3 intercepts. In other words, a quartic could look like this. And I didn't mean 3 intercepts, I meant 3 local maximum and minimum. They're preparing you for calculus here. And in calculus, what's very important is how many minimums and maximums we have. Well, there's 3 of them. It's always one less than what your function is. In other words, if I had a 5th degree function, I might have 4 local maximum. If I have a quartic, the most I can have is 3. If I have a cubic, the most I can have is 2. And if I have a quadratic, it's always a parabola. Well, that's 1 only. 1 local minimum. Right there. So this concept of minimums and maximums is very important for calculus. And you always end up with the maximum you can have is 1 less than the functions. Okay?
Okay.
So, hold on a moment. So let's see. What we figured out was that x had to either be -1 or +1. In other words, we know the function goes through there. Those are the x-intercepts. Furthermore, they're each squared. So we know that it doesn't go through the axis, it kisses the axis. In other words, it's going to look something like this. Both of those x-intercepts are going to be points that kiss the x-axis. Now, why did I start it from up here rather than down there? Well, if you let x go to -infinity, you have -infinity squared times -infinity squared, which is +infinity, which is negative. It looks like I drew it wrong. Yeah, instead of like that, it must look like this. Now, let's talk about end behavior. You know what end behavior means?
Well, what?
End behavior.
No.
As x goes to either positive or negative infinity, that's what you care about, because that determines whether this comes from negative infinity or positive infinity. Notice the first way I drew it. First way I drew it was like this. But can that be correct? In other words, as x goes to negative infinity, what does this function go to? Plug in negative infinity for x and then square it. Do you not get that?
Now I get that, because then the negative.
Right. In other words, when x is negative infinity and you add 1 to it and square it, you get positive infinity. When x is negative infinity, you square it and you get positive infinity. But then after you multiply positive infinity times positive infinity, you get positive infinity. You stick a negative sign in front of it, and it has to come from this point here. It can't come from the top left. In other words, it's very important to understand what end behavior is, because it makes the difference on whether I plot the black line or the blue line. And I made a mistake with the blue line. The end behavior is as x goes to negative infinity, y goes to negative infinity. So it has to start from the bottom. Okay.
That makes sense.
Now, they want 1 point, so this black line is the correct line. Let's erase everything else. That's the correct line. Now, how can I figure out that point right there? Because I want at least 1 point between the x-intercepts. Well, I've got the two x-intercepts on there. The easiest point to get is going to be the y-intercept. What does it mean when I say what the y-intercept is?
When x is at 0.
Yeah. So plug in 0 for x and figure out what y is.
You should get -1.
Correct. And that is this point right here. So that point is 0, -1. And that answers their full question. But let me emphasize here that the most important part of this problem, well, this was really a good question because it invoked a lot of mathematics. In other words, the fact that each of these was squared means that your x-intercepts don't cross the axis there. If it's an even power, then they kiss the axis. If it's an odd power, 1, 3, or 5, they go through the axis. So with both of these, I know they have to kiss the axis. Okay? And I also know that it's a quartic. So I'm going to have it probably 3 local minimums and maximums, and I do. I have that. Hold on. I have, that's a local maximum, that's a local minimum, and that's a local maximum. You know what I mean by those terms?
Yes, I do.
Okay. So that tells me a lot, that I have 3 local maximums or minimums at most, because it's a quartic, and that each of the zeros are going to kiss the axis, not cross it. And the end behavior. Well, the only thing you need to figure out the end behavior is substitute negative infinity for x and figure out whether it comes from negative infinity or positive infinity. Well, the first time I did this problem, I came from positive infinity because that's my natural orientation. But when I examined it closer, I realized it had to come from negative infinity. And end. In other words, when x is negative infinity, y is negative infinity. And when x is positive infinity, y is negative infinity.
Okay.
Hold on. Now this looks like a quartic, correct?
Mm-hmm.
In actuality, it is a quadratic in disguise. And you want to learn to recognize these. Very important to recognize these. Okay? Why do I say it's a quadratic in disguise? Because this term is the square of this term. And that's what makes a quadratic. Even though we're looking at a quartic, we can think of it as a quadratic. And the best way to do that is to use something called U substitution. Okay. Have you heard of this term, U substitution?
No, I haven't.
Well, get used to it because you're going to get it more and more when you get into calculus. If I let u equal x squared, which makes u squared equal x to the fourth, then what I'm really looking at here is u squared minus 10u plus 9. Can you factor that?
Yeah.
Into what?
X minus 9, x minus...
Let's stay with u for the moment.
U minus 9, u minus 1.
Now go back and substitute for u. What is u?
X.
It's x squared. So it's x squared minus 9 times x squared minus 1. Well, each of those, in other words, there's our answer. Well, not quite, because we can factor it further. What's x squared minus 9 equal to?
X plus 3, x minus 3.
And what's x squared minus 1 equal to?
X minus 1, x plus 1.
So there's your 4 solutions. What are they? If I'm trying to find how to graph this, what are my zeros?
You have plus or minus 3 and plus or minus 1.
So if I'm graphing that, there's plus or minus 3, there's plus or minus 1. So I know it has to go through those 4 points. Now, it's either going to look like this, right? Notice that this has 3 local minimums and maximums, or it's going to look like this. Depending on the end behavior. In other words, it's one of these 2 curves. It's either the blue curve or the red curve. Well, how can I figure out the end behavior? When x goes to negative infinity, what is y?
Positive infinity.
Yeah, that means it has to be this curve, right? Because the top curve, when x goes to negative infinity, y goes to negative infinity. So this is not correct. So this is. So I can immediately draw the curve. It's got to do this. Now, how did I know that it didn't kiss? In other words, how do I know that these x-intercepts, it crossed the x-axis? Well, because...
You don't have the dual.
Well, each of these is to the 1 power, right?
Mm-hmm.
And that being the case, that's an odd number, 1, and so it has to cross the x-axis. Whenever your intercepts are an odd power, it crosses the x-axis. When they are an even power, it kisses the x-axis. Well, every one of these is an odd power, so I know that at this point it's got to go through the axis. Same thing there, same thing there, same thing there. I know it has at most 3 local minimums and maximums. So the graph that I've drawn looks pretty good. That should, hold on. That should be it. Now, last part of this question. Label at least one point between, what's the easiest point to label?
Probably 0.
X equals 0. So what is that point when x equals 0?
It should just be 9.
Yeah. Whenever you're looking at a polynomial like this, and you're plugging in x equals 0, then the only term that matters is the constant. Every other term goes to 0. So this point right here has to be 0, 9. And that's all they need. That's the graph. That's one point. Now, obviously, you could label any point you want, although it's tough to know exactly what the x-coordinate is on that, and it's tough to know what the x-coordinate is on that. So the easiest point to label is going to be where the x-coordinate is clearly 0, and that's the easiest arithmetic to do. In other words, when you plug in x equals 0 into this function, the first 2 terms disappear and you have 9.
Okay.
Okay. All right, the next one. Let's talk about factoring cubics. Let's ignore the negative sign for a moment. Hold on, let me change this. And there's a reason I want to ignore that. Do you know how to factor cubics?
Wouldn't you like split it up into 2 halves?
Yeah, in other words, you haven't figured out how to factor cubics yet. They haven't taught it to you. And believe me that it's one of the toughest things there is to do in algebra, except in one situation, and that's where you can group it. Well, I can group this. In other words, I can group that by grouping it, I mean put it like that. And I can group the rest of it, which is what?
4x. Yeah, 4x plus 16.
Is it really? In other words, are those two the same thing? What you always have to do in math is make sure that as you're manipulating a function, you do not change it. There is a whole lot of stuff you have to do to functions to get them in the proper format. And the most important thing that you can be thinking of is, I cannot change the function. Is function 2 the same as function 1?
Yes.
Well, hold on. This negative sign has to be distributed to both terms. So it would be minus 4x minus 16. Therefore, that needs to be a negative sign. Now, can you see where function 2 is exactly the same as function 1?
Yeah.
That's what's important. If it's changed, you've made a mistake. Okay? And this is a huge concept in math. Every single time you manipulate a function, you should check to make sure you have not changed it. Now, in the first set of parentheses, what can I do? What can I factor out of that? What's the greatest common factor?
The greatest common factor would be x squared.
Leaving?
X minus 4.
And in the right term?
4.
Leaving?
X minus 4.
Now, the only reason that factoring by grouping works is because these two terms are exactly the same. If they are not, then this is not going to work. Okay? And what you have to look for when you're factoring cubics is the ratio of the coefficients. In other words, the ratio of this coefficient to that coefficient has to be the same as the ratio of that coefficient to that coefficient. Otherwise, grouping is not going to work. And I mean that absolutely. If they are not exactly equal, then grouping cannot be used. So the only time you can consider grouping to solve a cubic is if the ratio of the x cubed term to the x squared term is the same as the ratio of the x coefficient to the constant. And in this case, they're both negative 1/4, which means grouping's going to work. And that's the only time it works. And when it doesn't work, trust me, it's a 30-minute problem. Okay? So you haven't gotten to that yet. You will. But when grouping works, it's only a 5-minute problem. Now, hold on. What do I do at this point? And this is not all that obvious. Once I have it down to this step right here.
I'm not very sure.
What's the greatest common factor?
4.
X minus 4. And this is different because you're not used to factoring out binomial terms. So far in your entire math history, you've only factored out monomial terms. You've maybe factored out an x or an x squared or a 2x cubed, something like that. But you've probably never ever factored out a binomial term like x minus 4. Well, if I factor out x minus 4, what's left behind?
X squared minus 4.
Yeah, and you see how that works? In other words, you see that 1 is equal to 2?
Yeah.
Okay. Now, let's finish 2. I have x minus 4 and finish factoring x squared minus 4.
So your x value should be positive 4 and x equals plus or minus 2.
Correct. And those are your 3 intercepts. Now, there's a minus sign still, right there.
What is it?
Well, I disregarded it because at this point, we don't really care that it's a minus or a plus in front of that. It's going to make a difference when we go to graph it, for sure. So, first of all, let's figure out how many x-intercepts do we have?
You have 3.
Correct. At where?
1 at negative 2, positive 2, and 4.
Now, we're looking at a quartic, right? In other words, this is number 3. Well, which one? No, this is number 2. Can you tell that that's a quartic?
Yes.
Okay. Which means we're going to have 3 minimums and maximums. And in fact, none of these kiss the x-axis. They all go through it. So there's only 2 choices. It's going to look like this. You see where that's a possibility?
Uh-huh.
Or it's going to look like this. So the only thing, in other words, notice that each of these x-intercepts goes through the x-axis. It does not kiss it and bounce off. So the only difference between the black line and the red line is the end behavior. In other words, if we can figure out whether it's that or that when x goes to negative infinity, we'll have our answer. Well, what do we have when x goes to negative infinity?
Negative is y.
What does y go to when x goes to negative infinity?
Oh, positive infinity.
Correct. Because you have a negative infinity times a negative infinity times a negative infinity, which is negative infinity, times a negative sign, which is positive infinity. Which means this is the correct left-hand end behavior. And if you plug in, hold on. If you plug in positive infinity for x, you get negative infinity. So I've made a mistake. The right-hand inside should go that way. Question is, how? We're doing number 3, not number 2. Sorry, I got mixed up for a moment. In number 3, because it's x to the 4th and x squared, the right-hand end behavior has to be positive infinity also, right? So this is actually correct. And this is the correct curve, the orange curve. In other words, the end behavior fits when x goes to negative infinity, and the end behavior fits when x goes to positive infinity. Now, they want at least 1 point. Dang, what am I doing wrong here? I'm doing the wrong problem, aren't I?
I think we're doing number 5.
Yeah, you're right. I'm sorry.
It's alright.
Number 5. First of all, let's talk about end behavior. End behavior is only affected by the highest degree polynomial. I don't care about this minus 4x squared. I don't care about the minus 4x. I don't care about the plus 16. When I plug negative infinity in for x, it's this x cubed that I care about. Well, x cubed is negative infinity, but when I put a negative sign in front of it, it becomes positive infinity. And same thing when I put positive infinity there. It's positive infinity with a negative sign in front of it. So it's got to go down like that. All right, hold on a minute. Are you familiar with Wolfram Alpha?
Yeah.
You know, it's a great thing to use when you are online or even if you're in class. I mean, Wolfram Alpha does a bunch of things that your calculator probably doesn't do. Let me show you. In other words, it will graph this function. More importantly, it will tell us what we're graphing, which is huge. Because what kind of calculator do you have?
TI-84, I think.
Yeah, when you plug it into a TI-84, it doesn't tell you what you plugged in. But notice Wolfram Alpha will. It tells us exactly what we plugged in. So we know we typed it in correctly. And this is the graph. And notice that when x is equal to 0, we should have minus 16, which is right there, that point right there.
Mm.
And we have our zeros at minus 2, plus 2, plus 4, which is exactly where we calculated it. The only mistake I made was I had 3 local minimums and maximums, and this curve only has 2. And that's an important lesson. When you have a quartic, you're not guaranteed to have 3. You can have 2, you can even have 1. But the most you can have is 3.
Mm-hmm.
Well, in this particular function, they only have 2. And I guess, I'm just thinking now that when you have a quartic that lends itself to grouping, like this one did, you don't have as many, you only have 2 local maximums instead of 3. And figuring out the point between your x-intercepts, in other words, we had no problem figuring out the x-intercepts, there were 3 of them, but figuring out this point is actually relatively easy also. You just substitute 0 for x and you get minus 16. So that point is obvious. But what's different is the fact that there's only 2 local extrema. And this might seem like a subtle point, but once you get into calculus, this is huge. Calculus is all about these local extrema. In other words, local minimums right there and local maximums right there. When I say local, I mean that it's only within a region. In other words, only if you're looking at this part of the graph is that a minimum, and only if you're looking at this part of the graph is that a maximum. Because if I continue this function in both directions, neither one of those are absolute minimums or absolute maximums. And this second curve is just a different scale, you can notice. And you can't hardly even see the minimums and maximums. One of the beauties of Wolfram Alpha, in case you're not aware of it, it's actually much better than your TI-84. Notice immediately what it did. It gave me the 3 zeros. Minus 2, plus 2, and 4. So the fact that it gives you the zeros is huge. That's one of the most important things you can have in math, is where are the zeros of this polynomial? And you can get that from your TI-84, but you have to go into trace, request zeros, and you have to hit about 10 different key strikes to get the zeros. So the zeros that Wolfram Alpha give you are pretty key. They also give you all kinds of other stuff that you're not into yet, like derivatives, integrals, maximums, minimums. So Wolfram Alpha is a really cool math tool. And if you could actually take tests and they would allow you to use it, you should, as opposed to your TI-84. The most important thing that Wolfram Alpha does is it shows you the function you typed in. And that's pretty huge because your TI-84 doesn't show that. And it's not that easy to type it incorrectly. I mean, sometimes if you have a lot of nested parentheses, it's very difficult to type it in. So getting a visual feedback on what you actually typed in is pretty huge.
Mm-hmm.
All right.
It also gives you the domain and range, which is nice too.
Let's see, we started at 3, so we only have 15 minutes, and looks like we have a lot more than 15 minutes worth of problems. Do you want to direct me as to which of these you want to go to next?
Could we do number 10, because it has an inequality?
Yeah. That's a good point, because inequalities are completely different than equations when you're doing it like this. First of all, factor that. Whenever you see a quadratic, always think factoring. If you can factor it, you should.
So you should get x plus 6 x minus 3.
X minus 6, x plus 3. Remember that the biggest factor has to go with the sign of the middle term.
Okay.
Well, the biggest factor is 6, so it has to go with the negative sign. Now, once you get to this point, it's not even that obvious on how to proceed, but the way you want to proceed is you draw a line chart. Okay? And it doesn't matter whether you have two linear terms multiplied by one another, or even if you had two linear terms divided by one another. If I wanted to solve that, I would need a line chart. Okay? So remember line charts, because they're going to be needed to solve any problems like this, whether you have two linear terms multiplied or divided together. Now, the first point is, what are my critical points? Which is whatever makes these things 0.
Your critical points would be -3 and +6.
Tell me what the critical points on this would be.
-7 and -8.
Okay, good. In other words, your critical points are whatever makes either of these 0. Now, you take your critical points and you put them on your line chart, like this. And I don't put 0 on there for a very good reason. That's not one of the critical points. Okay? Now, the next trick is to test points to the left of -3. Well, pick a point to the left of -3.
-5.
Okay? When x is -5, what is x minus 6?
-11.
And the only thing we care about is its sign. I don't care that it's -11 or -111. The fact is it's negative. Now when x is -5, what is x plus 3?
It should be -2.
Now what's a negative times a negative?
A positive.
which means every point to the left of -3 is positive. No matter what x value I choose, I could choose -100, and I still get a negative times a negative, which becomes a positive. Okay, now we need to check this area here. Pick a point between -3 and 6.
0.
Always the best point if you can pick it. What's x minus 6 when x is 0?
-6.
Just negative. Again, I don't care about the 6. I'm only concerned about the sign. What's x plus 3 when x is 0?
3. So positive.
Plus. Now what's negative times positive?
Negative times positive is negative.
So everywhere in that area between -3 and 6 is negative. Now finally, the last step, what about pick a number greater than 6?
10.
Okay. I would almost suggest always pick a number that's just exactly 1.
So 7.
Yeah, just because it makes the math easier.
Okay.
In other words, you could pick 100, wouldn't matter, but 7's easier to do the arithmetic. Well, when x is 7, what is x minus 6? Positive or negative?
Positive.
What's x plus 3?
Positive.
Which means plus times plus is plus. That is greater than 0, so I can make that statement. Now, let's go back to the original equations. I'm looking for everything that's plus greater than 0. Well, that's that and that. So my solution is what? X is less than what? Or x is greater than what?
X is less than -3 and x is greater than 6.
And there's your solution. Now, question said what? It said, solve the following by factoring. Well, we just did. We completely solved it. And give it to me in interval notation. You know what that is?
No.
Interval notation would be x is less than -3, so I can go all the way to -infinity to -3 in union with 6 to infinity. In other words, this interval notation covers those intervals. And if you haven't learned it yet, I'd be surprised if you don't get it. Interval notation is pretty standard in Common Core. You go to Mullen, right?
Yeah.
Even Mullen's going to give you interval notation. They'll give it to you before anybody else will. So you want to know interval notation. That's what that is. Okay? And you can see why that's the proper answer. In other words, x can be anywhere from -infinity to -3, but not including -3. Or it can be anywhere from 6 to infinity, but not including 6. Okay? If that was a greater than or equal to, then that would be a bracket. That's the difference.
All right.
Okay? Now, a couple of these, calculator, solved by factoring. Let's take a look at this first one here. This isn't that easy. Is that a quadratic in disguise?
Yeah.
Okay. When you see a quadratic in disguise, always think U substitution. What am I going to let U equal to? Hold on, there's an X right there.
X squared.
No, it's whatever the middle term is.
So X
X
negative 1.
minus 1. Now what's U squared? If U is equal to X to the minus 1, what's U squared?
X to the negative 2.
Yes, that's what we're looking at here. This is a quadratic in disguise. And you can always solve quadratics in disguise by using this concept of U substitution. Whether they've taught it to you or not doesn't really matter. U substitution turns this thing into 3U squared, right? Plus 3U minus 18 equals 0. And here's our quadratic. It only looked like whatever this is. I can actually turn it into a quadratic. And how do I factor that?
Oh, you have 3U and U and 1.
Factors of 18.
Yeah, 6 and 3.
That's what I would always start with. Always the closest two factors. It could be 9 and 2. It could be 18 and 1. But I'm going to start with 6 and 3. I'm going to start randomly. Does that produce the correct middle term?
Yes.
Hold on a moment. I made a mistake here. It's a negative 18, so if this is plus minus, this has to be minus plus. You understand why?
No.
Okay, now, does that produce the correct middle term?
Yes.
Actually, no. In other words, if I multiply the insides, I get plus 6u. Multiply the outsides, I get minus 9u. That gives me a minus 3u. Well, what does that tell me? I got the right number, but the wrong sign. When you get the right number, but the wrong sign, it means you merely have to move your number down to the other sign. In other words, that 6 and that 3 go here. Now, does that give you the right middle term?
Yes.
Yeah. In other words, that's plus 9u, that's plus 3u. That's our correct middle term. Therefore, we have factored it properly. Now, I'm not quite done. In other words, I haven't really solved yet anything. What's the next step?
Plugging back in the X's.
Well, or we could solve for u. What's u equal to?
U equals 2 and negative 3.
Okay. Now let's plug in. Well, u was x to the minus 1. So we have x to the minus 1 equals 2. Or x to the minus 1 equals negative 3. Well, if x to the minus 1 equals 2, what does x equal?
I'm not sure.
1/2. X to the minus 1 means 1 over x. So if 1 over x equals 2, x equals 1/2.
Mm-hmm.
Okay? if x to the minus 1, remember we're still dealing with x to the minus 1, if it's equal to minus 3, what is x equal to?
Negative 1/3.
Yeah. And there's your two solutions to this problem. In other words, those are your two zeros. Are x is at 1/2 and x is at minus 1/3. And that's all this problem wanted, was solve it by factoring. And that's exactly what we did. Okay? What we're looking for when we see problems like this is, are we looking at quadratics in disguise? Notice that 9 is a quadratic in disguise, right? In other words, the middle term is x to the 1/2. The term on the left is x to the 1. Well, as long as x to the 1 is the square of x to the 1/2, then you have a quadratic in disguise. A quadratic is always where the first term is the square of the middle term. Same with 7. The square of y squared is y to the 4th. So that is a quadratic in disguise. The same with 6. And actually the same with number 8. We don't have time to go over it, but number 8, well, you can actually factor out an x squared minus 9, right, with number 8?
So would it just be x squared plus 5x minus 14 equals in parentheses and squared minus 9 is it?
In other words, you factor it out just like we factored out a binomial on number 5.
Okay.
And then, of course, x squared minus 9 factors, and x squared plus 5x minus 14 factors. So you're going to end up with 4 different factors. So there are 4 solutions to number 8. And let's check. Should we have 4 solutions? Well, x squared times x squared is x to the 4th. So yes, the highest degree polynomial is going to be x to the 4th if we were to multiply this whole thing out. So we would expect 4 solutions. You usually have the number of solutions as you have the degree of the quadratic.
Okay.
Okay, there's a lot of other stuff on here. This is quite a bit of material. You might, I don't know when you're going to be tested on this, but you might want to schedule another session. This is like at least 2 hours of tutoring to go through all of these problems.
Oh geez.
But that's all. Well, we've done 1 hour of tutoring. We got through the first 10 questions, basically. And there's another 7 questions. But this is a lot of pre-calc. I would say normally I'm covering these kind of problems in 3 sessions. In other words, it's that much material.
Mm-hmm.
All right, Jake.
Thank you.
You're welcome. I hope I've been helpful, and
Okay, you were very helpful. Thank you.
I will talk to you next time.